We just spent some time reviewing exponential functions, and now we're going to get into the calculus of them. So the next section, 4.3, is all about the derivatives of exponential functions. And we're just going to learn the derivative of the natural exponential function, which is the one that has base e, which is that number, irrational, between 2 and 3. It has a really nice derivative, as you'll see. So that is the only exponential function that you'll be responsible for knowing how to find the derivative of, although there are formulas for any base in general. We have two rules in this section. The first one is just what is the derivative of just plain old e to the x, right? Just the baseline natural exponential function. So that's our first rule. So the derivative of the function f of x equals e to the x. Okay, remember an exponential function is one that has x, the variable, in its exponent. And the natural exponential function, again, has a base of the number e. It looks like a variable, but remember e is just a number. So the reason why I say that this is a really nice derivative is because the derivative is actually just itself. Nothing happens when you find the derivative of this. You just get itself back. It's the only function with this property. Okay, so in other words, if f of x equals e to the x, then f prime of x, the derivative, is also e to the x. F double prime of x, the second derivative, would also be e to the x. The third derivative would also be e to the x. The 900th derivative would be e to the x. So if you just have e to the x, its derivative is simply itself. So I just want to note to you that normally when you see something that has an exponent, we think of the simple power rule, right? Bringing the exponent down, multiplying, and subtracting 1 from the power. That is only when we have a variable in the base and a number in the exponent, right? That does not apply for exponential functions. So what I'm saying in symbols is that the derivative of e to the x is not ever x times e to the x minus 1. Okay, that does not work, again, for exponential functions. So don't make it even more complicated than it needs to be. Like the derivative of e to the x is just itself. So before we get to the second rule in this section, let us look at finding the slope of the tangent lines using this, this derivative here to look at the curve of y equals e to the x. Okay, so here's a graph of y equals e to the x. We see that it is like a rising exponential function. We've got growth because the x here is positive. This is a base that's bigger than 1. And so there's some points on here. We're going to, in particular, look at 0, 1, right? So if we plug a 0 in for x, we get e to the 0, which is 1. So that's a point on the graph right here. And then 1, e. So if we plug a 1 in for x, we get e to the first. So we get e out for y. So that point is, here's 1. And then the point on the curve is here. And you can see here's 3, and that's a little bit below. Like we know, e is around 2.7. Okay, so let's first look at the point 0, 1. So again, that point's right here. We want to find the slope of the tangent line to y equals e to the x. So that's this black curve here. Okay, the slope of the tangent line at this green point. So we can, it's been a while since we sketched tangent lines, but it's the one that goes through this point and has just the right slope. So it's going to look something like this. It's going to look something like that. That's a good tangent line at the point 0, 1. What we want to know is the slope of this line. Right, so remember that one of the key purposes or meanings of the derivative is that it gives us exactly what we're looking for here. It gives us the slope of the tangent line to a curve at any point. Okay, so if we have y equals e to the x, then the derivative y prime is also e to the x, just based on this rule over here, right? Our first rule in this section. Okay, if we want to find the slope at 0, 1, we're going to plug in a 0 for x. So we'll say y prime of 0, that's e to the 0, and that's 1. Okay, so what that means is that the slope of this green line here is equal to 1. If we look at our other point, 1, e, let's make this one pink, how about? So that point, so here's 1. The point on the curve we're looking at is right here. So that y value out is e. And the tangent line, if we sketched it in, it might look something like this. Okay, and again, so I'll label this point here. So here's 1, e. So the slope is still positive. It's probably bigger, but we can find the exact slope by plugging into the derivative. So let's do at 1, e. What's the value of the derivative at our x value here, which is 1? Okay, so we'll plug in 1 for x into the derivative. We'll get e to the first, and that's just e. All right, so that means that the slope of this line is exactly equal to e, which again is around 2 points of it. Okay, so this function is really weird because the coordinate, the actual height of the function, is equal to the slope of the tangent line at that point, right? The height of the function at 0, 1 is 1, and the slope is also 1 here. So that's what's kind of really neat about this function. At 1, e, right, the y value where the height is e, and the tangent line at 1, e, it has slope of e. So at any single coordinate on this graph, graphically, the derivative being itself, that's kind of what that means, that the y coordinate is equal to the slope of the tangent line. All right, so we do want to be able to differentiate functions that are more than just e to the x. So what happens if we have e to the 2x, or e to the negative x, or maybe 2e to the x, or maybe even e to the x squared, or something like that? So combining this with the chain rule, so combining the previous rule right here, the first one that we just talked about, with the chain rule. I know in the past, we kind of said the chain rule and the general power rule are basically the same. The chain rule is a more general kind of idea that allows us to differentiate function compositions. So if we are going to find the derivative of e to a function of x, meaning that the exponent isn't just x, it's something more complicated, but it does involve x. It's just, again, maybe something like 2x or x squared or something like that. We still get itself, but then we have to, with the chain rule, okay, so what we're looking at, I'm going to finish this sentence in a second. So what we've got in symbols, this is going to continue on here, but just to start out, so what are we actually talking about? E to, I'm going to use p for power. So e to the p, where this p here is a function of x. Okay, so we've got this outer function that is the exponential function. So we still differentiate the outer function first. And that derivative of e to anything is itself. But then with the chain rule, we have to go inside to the inner function and multiply by its derivative. The inner function is the whatever is put into the exponent. Okay, so this is going to be, okay, so the derivative of e to a function of x is itself times the derivative of the exponent, or the power. Okay, so in this formula here, we just have to multiply this. Okay, we're no longer in the exponent anymore. This will just be times p prime times the derivative of the exponent. And that's how we handle something that's a little more complicated than just e to the x. So all of our rules that we know and love and appreciate about derivatives still apply. We just have one more function that we can differentiate, that we can throw into our toolbox. So let's practice finding the derivatives of some exponential functions. I've got a bunch here, so let's get started with just e to the 2x. Okay, so here, if you want to identify what the p is, or the power, right? That's what I'm referring to is the 2x, right? So p is 2x. Okay, so if we go back up just for a sec, our formula here. Okay, this is really important to know how this works. Okay, the derivative of the exponent, or p prime, right? That's 2. The derivative of 2x is 2. So now when we differentiate the entire thing, okay, we get itself, we get e to the 2x, but this just needs to be multiplied by the derivative of 2x, which is 2. Okay, so we've got e to the p itself, but then you just have to multiply by the derivative of what's in the exponent. To simplify, there's not often too much you can do, but if the derivative is a single term like that, it might just be nicer to write that like 2e to the 2x instead of e to the 2x times 2. Okay, so here we go. Here is the derivative of e to the 2x. E to the 3x, you might guess that that's derivative is 3e to the 3x. Right? E to the 4x would be 4e to the 4x. So here in example 2, I've got something that's a little more complex. We've got 5e to the 1 minus 3x squared plus 2x cubed. I'm just going to kind of separate these. It's a little crowded here. Okay. So in finding these derivatives, the first thing you want to do is, well, we're going to differentiate this whole thing. So we could say, all right, I know that the derivative of e to anything is itself. Now this 5 in the front, this is a constant multiple. Remember, when we differentiate constant multiples, these just stay alone, or they stay and multiply by the derivative. So this is going to just continue through and still be multiplied by the derivative of e to all of that stuff. Okay, so the derivative of e to all that stuff is itself, so we get e to the 1 minus 3x squared plus 2x to the third. Okay, and then here is the power. Here's p in the formula. So all we have to do is multiply this entire thing by p prime, or by the derivative of the exponent. So you can do this on the side if you want, or if you can just see what that is and write that down, that's fine. But p prime here is going to be the derivative of 1 is 0, minus the derivative of 3x squared, so that's negative 6x, plus the derivative of 2x cubed, so that's plus 6x squared, I believe. Okay, so this whole thing here, we need parentheses, is going to be multiplied by negative 6x plus 6x squared. And that's it. You don't have to, like I said, often you don't have to simplify things like this. There is some factoring that you could do here, but for just differentiating, you want to be okay with that at this point in time. So, okay, we leave it alone exactly as it is, right? See, we have the same function here, and then we just multiply by the derivative of the power. And that's it. Okay, so looking down here, we've got example number 3. This is 4 over e to the x. 4 over e to the x. Now, in this case, we don't have e to the x, like kind of, I mean, it's in the denominator. And the rule doesn't say anything about that. It just says e to something. How do we differentiate that? Now, when we have a fraction, we have the quotient rule. We also know that you can't just differentiate the top and differentiate the bottom and then divide them, right? This isn't going to be the derivative of 4 is 0, the derivative of e to the x is e to the x, right? That would just be 0, and that doesn't work that way, right? So what we have to do is rewrite this. We have to rewrite this and get the e out of the exponent. The e is not in the exponent, sorry, out of the denominator. Sometimes my brain just like throws out math words there when it's tired. So out of the denominator, so let's bring up the e to the x. We can do that if we just negate the exponent, right? So this will just be 4e to the negative x. Now this looks like something that we can use our new rule on. Okay, we've got a constant multiple here of the 4. Okay, the p, the power is the negative x. Okay, so p prime, the derivative of that is negative 1. So when you find the derivative of the entire function, okay, the 4 stays, that's a constant multiple, and we multiply it by the derivative of e to the negative x. The derivative of e to anything is itself, so the derivative of e to the negative x will be e to the negative x, then multiplied by the derivative of the power, so by p prime. So this will be times a negative 1. Now we can simplify this. Often one step is nice to take, especially if you can just multiply a number and another number together. So this will look like negative 4e to the negative x. Or if you want, you could write that as negative 4 over e to the x, but this is totally fine to leave it like this. So I hope you're getting the hang of this so far, but we will continue on and do a few more examples. So let's look at number 4, which is f of x equals 3. This is weird. 3 times the, how would I say, the xth root of e. The xth root of e. All right, so we have to write this. We have to remember our exponent rules, and we have to write this as e to something. So remember that whenever we have a root, we can write that as a power. Okay, this 3 isn't involved in the root, so I'm just going to leave that there. But if you think about like the cube root of x, right? This would be x to the 1/3 power. So if we have the xth root of e, okay, we're going to leave the e and we're going to convert that xth root to an exponent. And whatever root you have, the exponent becomes 1 over that root. So it'll be 1 over x. Now this looks like something that we can find the derivative of using our rule. Okay, so again, we've got another constant multiple with the 3. So when we differentiate this, the 3 is going to stay. Okay, the derivative of e to the 1 over x is itself times the derivative of 1 over x. Okay, so now here's the p. So to find p prime, we have to think about differentiating 1 over x. I would not suggest using the quotient rule on 1 over x. I would think of 1 over x as x to the negative 1. Right, just bringing that up and rewriting it with a negative power so that now we can just use the power rule. So we'll bring the negative 1 down and multiply, and we'll subtract 1 from the exponent. So it'll be negative x to the negative 2, or we can write that as negative 1 over x squared. Okay, so the derivative of the exponent here, that's the only thing we were missing in our overall derivative. So this will all be multiplied by negative 1 over x to the second. Okay, now the last thing I would do is maybe just multiply these together and write as a single fraction. So here's all the stuff that's kind of in the numerator. They're all single terms. We can just multiply them all together. And then this x squared will stay in the denominator. So this could look like negative 3 e to the 1 over x over x squared. All right, example number 5. Example number 5 is f of x equals x cubed times e to the negative 2x minus x times e to the negative 2x. All right, so what we have here, it looks like, I mean, we have two parts to this, right? We've got this part and we've got this part. Now, if we just think about differentiating this first part here, right? We know with minus, we can differentiate each of the things separately. So let's just look at this first part first. We've got x cubed times e to the negative 2x. What we've got here is a product of two things that have x's in there. So in order to differentiate this first part, we are going to need the product rule. And I think I actually made this a little more complicated than I wanted it to be. So let's just kind of scratch out that. Let's just take it little piece by piece and let's just do this first function, or the first half of the original one I had written here. So let's do x cubed times e to the negative 2x. All right, so we do need the product rule. So let's remind ourselves what that looks like. So we normally use u and v. Okay, so here's u. Okay, here's v. Okay, the product rule says, well, let's see what it says. So we take, we need the derivatives of each of these parts, right? So u prime will be 3x squared. And v prime, here's where we need our new rule. Now, I know there's a lot of letters getting involved here. So if you want to kind of bypass this writing down p and p prime, you can. But if this helps you, you can do that too. So here's the p, right? The power is negative 2x. The derivative of that is negative 2. So when we differentiate e to the negative 2x, right, it's going to be itself times p prime, the derivative of the power, times power prime. Okay, and if we just simplify that, that'll look like negative 2 e to the negative 2x. Okay, so if we take the derivative now of the entire function, okay, the way that the product rule goes is we take the first times the derivative of the second, so u times v prime, so that'll be x to the third times negative 2 e to the negative 2x. Then we add the second times the derivative of the first. Okay, so we take now these pieces, so u prime times v. Okay, so it'll be 3x squared times e to the negative 2x. Now, in terms of simplifying this, I mean, if you can get here, that's great. We could do at least one step of simplification. Normally the way that we write things when we've got a bunch of stuff like this multiplied is the number comes first, the -2, then the power of x, then the e. So we can write that first chunk a little more cleanly as -2 x cubed times e to the -2x. And the second chunk here already has that format, so we can just leave it like that. Again, this is a great place to be. It's a nice place to stop, but we could factor this and simplify it a little more. So the one thing that I might push us to do is to factor out GCF. Right, but the calculus is over already, so this is just a little bit of algebra. So we got a GCF. Well, what is the GCF? If we look through, we've got x is here. Well, the numbers don't have any factors in common, so x cubed and x squared, so we could take out an x squared. And they both have an e to the -2x. So we can take out an x squared times e to the -2x. What we're left with here, we'll have a -2 and x to the first left over, and then that e is factored out, so it'll be -2x. Then in the second piece here, we'll have a 3 left over, x squared and the e were factored out, so we'll have +3. And there's our a more fully simplified or fully factored derivative. All right, so moving on, I've got 2 more examples here, and then we will look at some applications of this. So here's example number 6. We just combined this new rule with the product rule. Here's an example of combining this new rule with the quotient rule. Okay, so we've got some stuff with x over some other stuff with x, right? Numerator and denominator both are functions involving x. So we absolutely 100% need the quotient rule. So we've got our numerator here, and we've got our denominator here. Now we need the derivatives of each of these. So the numerator derivative, right, the derivative of e to the x, that's just itself. So that'll be e to the x. Okay, the denominator derivative, the derivative of 1 here is 0. Okay, then we've got minus the derivative of e to the -x. So we've got then minus e to the -x's derivative, which is itself. Then we have to multiply this by the derivative of the exponent. So the derivative of -x is -1. And if we multiply these and simplify, we can multiply the negative, and that just becomes positive e to the -x. Okay, so now we get to put this together into the quotient rule, which is old stuff. So we'll have f prime of x. It's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom. And then that's all divided by the bottom squared. Okay, now to simplify the quotient rule results, you don't really ever want to FOIL out the denominator, but we do want to work with the numerator and see if we can simplify that in any way. So in this case, it looks like we could probably distribute the e to the x into here and here, and we can also figure out what this product is. Okay, so e to the x times e to the -x, those have the same base. So let's just come over here and see what that would be. So e to the x times e to the -x, they have the same base. So what that means is that we can add their powers together. Okay, so we'll do x plus -x. Okay, or x minus x. Now when you have x minus x, that's 0. So we have e to the 0, and so that comes out to be 1. Okay, so this whole second product here in the numerator, that's going to be equal to 1. And we're going to get the same thing when we distribute this e to the x into this factor here. Okay, so if we distribute this into here and into here, we're going to get an e to the x when we multiply it by the 1. Then when we distribute it into this e to the negative x and multiply, we'll just have minus a 1. Okay, then we're just going to subtract this product, which we saw over here, that's also equal to 1. So we have minus another 1. And again, we just leave the denominator factored like that. And the last thing that we could do is just to, we've got -1 minus 1. So why not just combine those? That's the same as minus 2. And there we go. Here is our fully factored derivative. All right, example number 7. This is an example using the general power rule alongside with the new rule that we learned today. All right, so the thing that we have here is some stuff raised to the third power. Right, whenever we have some stuff, right, some stuff here, I don't care what it is, but it's more than just x, and it's raised to a power, then we want to use the general power rule. So let's remember what that rule says. So this is the one where we've got the derivative of base to a power. Right, we bring the power down and multiply and subtract 1 from the exponent. Then we multiply by the derivative of the inside. So this is the general power rule. Okay, so we're going to, I know there's a lot of letters here. I think it's easiest if you can try to see what's happening, but if the letters help you, my hope is that it's helpful to have all of these, but it can get a little, I hope it doesn't hurt to have them, I guess is what I'm trying to say. So, you can kind of visualize this as, okay, the 3 is going to come down and multiply. We leave the inside the same. We subtract 1 from the exponent, so it'll become a 2. Okay, so that's the derivative of the outer function, or the outside. Okay, so the 3 comes down. We leave the base the same. And we subtract 1 from the exponent. Okay, that's this part here. Okay, we bring down the power, leave the base the same, subtract 1 from the exponent. Now we have to multiply by the derivative of the inside. Okay, the inner part here. The derivative of 3e to the negative x plus 1. Okay, so the derivative of 3e to the negative x plus 1, well, that 3 is a constant multiple, so that stays there. The derivative of e to the negative x is itself times the derivative of negative x, which is negative 1. Okay, then the derivative of 1, right, this one from right here, that derivative is 0. So there it is in its first, its first evolution here. Let's kind of try to simplify this. So we can say, I'm going to leave this here. I do just want to rewrite this maybe as negative 3e to the negative x. Now we don't really want to do anything with this thing that's squared, right? Order of operations, that stays. Or we can't go inside those exponent, the square here, unless we were to FOIL. But what we could do is multiply this negative 3e to the negative x times the 3. So it'll just be negative 9e to the negative x, 3e to the negative x plus 1, whole thing squared. Okay, so this, I've tried to give a variety of different ways that we can see these rules combined. Of course, there are many ways beyond this that you could have to take the derivative of something involving an exponential function. It could be something basic like this, e to a power or e to a power, or maybe you have to rewrite and get it to look like e to a power, like examples 3 and 4. Also keep in mind that we have the product rule, we have the quotient rule, and we have the general power rule. And so these can all be combined in many different ways. We're just adding a new function in our toolbox that we can now differentiate.